In the last video, we looked at 4 common free body diagram mistakes. The frustrating part is this. Once I see the correct diagram, the mistake feels obvious. But while I'm drawing it, I don't know if I've added a force that shouldn't be there, or missing a force, or pointed a force in the wrong direction. So today I'm going to show you a simple checklist that I use every time I draw a free body diagram. It's a process that helps you catch the most common free body diagram mistakes before they cost you marks. Once you learn this checklist, you can use it on almost any high school dynamics problem. Let's build a checklist. The first step is to choose exactly what your diagram is about. Before you draw a single arrow, decide what the system is. Is it block A? Is it block B? Or is it both blocks together? Once we have identified which object to work on, the next step is to select the forces from the candidates. Normally, these 5 forces are the ones you will use most often in high school dynamics. The gravity, applied force, the tension, normal force, and friction. If you can identify these 5 correctly, you will solve the vast majority of free body diagram questions in this course. There are other forces, but this belongs to more specialized situations. When a problem clearly shows a spring, a fluid, an electric field, or a magnetic field, the situation itself usually reminds you to consider those forces. So for today's video, we are not going to focus on those special cases. Now let me show you how to choose forces from those candidates. I don't start with a list, I start with the picture. Forces are not just arrows you remember, they are interactions you identify. So, instead of trying to memorize a force table, I want you to identify the interactions in the diagram. I start with the picture and I ask myself 2 questions. The first question is there a long-range interaction without touching the object? In most high school dynamics problem, the answer is yes, it's gravity. The Earth interacts with every object without touching it. So I include the gravitational force. And the second question is anything touching the object? In this case, for example, there's a rope is touching the block. So I'll include the tension force in the diagram. Anything else touching it? Yes, the floor. So I'll include the normal force in the diagram. And because the surface is rough, then I also include the friction force. Notice what I'm doing. I'm not inventing arrows. I'm identifying interactions and selecting the matching forces. Now let's put this process into action. We'll work through 3 different examples, and you will see that even though the situations look different, the process stays exactly the same. For every example, we'll do the same 2 steps. First, choose the system, and then identify the interactions and select the matching forces. Let's start with our first example. Here we have a box being pushed up a rough incline. So following our process, the first step is to decide what we are drawing the free body diagram for. In this example, we are drawing the free body diagram for the box. So I'm only going to include forces acting on the box. Next, let's move on to the second step. Let's start with the long-range interactions. Is there one? Yes, the Earth interacts with the box through gravity. So I'll draw the gravitational force. Now let's look at the contact interactions. What's touching the box? The person. The person is pushing the box, so I'll draw the applied force. What else is touching the box? The incline. The incline is supporting the box, so I'll draw the normal force. The surface is rough, so I will draw the friction force. The box is moving up the incline relative to the surface. Friction opposes that motion, so it points down the incline. And that's our free body diagram. Notice that I never had to memorize an inclined plane free body diagram. I simply look at the picture, identify the interactions, and the forces naturally followed. Now let's see if this exact same process works on a completely different problem. This time we have two objects. That means before we draw anything, we need to decide which object we are drawing the free diagram for. Let's start with block A. We're drawing the free body diagram for block A, so I'm going to identify what interacts with block A. Again, is there a long-range interaction? Yes, the Earth is pulling on block A, so I draw the gravitational force. Then what's touching block A? The table. The table supports the block, so I draw the normal force. Should I draw friction? Not this time. Here's an important word, frictionless. That immediately tells us we should not include a friction force. Anything else touching the block? Yes, the rope. The rope is pulling on the block, so I draw the tension force. That's the free body diagram for block A. Now let's draw the free body diagram for block B. Let's go through the same process. Is there a long-range interaction? Yes, the Earth pulls on block B, so I draw the gravitational force. Now let's look at the contact interactions. What's touching block B? The rope. The rope pulls on the block, so I draw the tension force. Anything else? No, nothing else is touching it. So that's it. That's the complete free body diagram for block B. Let's look at one final example. And this example asks us to draw the free body diagram for block A, for block B, and both blocks as a system. So let's start with block A. We are drawing the free body diagram for block A, so we'll only identify interactions involving block A. First, is there a long-range interaction? Yes, the Earth pulls on block A, so I'll draw the gravitational force. Now let's look at the contact interactions. What's touching block A? The block underneath it. The lower block is supporting block A, so I'll draw the normal force. And the contact also makes friction a force candidate. Now we need to determine its direction. Which way should the friction force point? This is where many students get confused. A lot of students look at the block and say, the block is moving to the right. So shouldn't friction point to the left? The answer is no. And here's why. Remember what we've been doing throughout this video. The most important thing is we don't start by thinking about the forces, we start by identifying the interactions. So ask yourself, what is block A interacting with? It's not interacting with the ground. It's interacting with the block underneath it. That means the motion we care about is not the block A's motion relative to the ground. It's block A's motion relative to the block underneath it. So, imagine the friction suddenly disappears. What would happen? The bottom block would accelerate forward. The top block would tend to stay where it is. That means, relative to the bottom block, the top block would slide backward. Friction always opposes that relative motion, so friction force on block A points forward. Notice how the interactions tells us what to compare. We compare block A with the object it's touching, not with the ground. That's why I keep asking what's touching the object. Because once you identify the interaction, you've also identified the only relative motion that matters for the friction. Now let's draw the free body diagram for block B. Again, we're only going to identify interactions involving block B. First, is there a long-range interaction? Yes, the Earth pulls on block B, so I draw the gravitational force. Now let's look at the contact interactions. What's touching block B? First, the floor. The floor is supporting block B. So I'll draw the normal force. The same contact also produces friction. So friction becomes a force candidate. Now we need to determine its direction. Relative to the floor, block B is moving to the right. Friction opposes that relative motion, so the friction force points to the left. Let's keep going. Is anything else touching block B? Yes, block A is also touching block B. Block A is pressing down on block B, so I'll draw another normal force. Notice that this one points downward because it's coming from the block above. And this same contact between block A and block B also makes friction a force candidate. Now let's determine its direction. Imagine the friction between the two blocks suddenly disappears. The bottom block would move forward, while the top block would tend to stay where it is. So relative to block A, block B would slide forward. And to oppose that relative motion, the friction force for block B points to the left. Anything else touching block B? The rope. The rope is pulling on block B, so I'll draw the tension force along the rope, which have a small angle from the horizon. And that's the free body diagram for block B. Now we'll finish the free body diagrams for both blocks, but let me ask you a question. Do we need all of this if our goal is simply to find the acceleration of the two blocks? Not necessarily. Sometimes there's a much simpler approach. Instead of treating the two blocks separately, let's treat them as a single object. In other words, we are going to draw one free body diagram for the entire system that involves both A and B. So following our process, the first step is to choose what we are drawing the free body diagram for. And this time, we are choosing both blocks together. Next, let's identify the interactions. First, is there a long-range interaction? Yes. So I'll draw the gravitational force in the diagram. Then, what's touching the system? The floor. The floor supports the entire system. So I'll draw the normal force. The system is moving to the right across the floor, so I'll draw the friction force. Since the friction opposes the motion between the floor and the system, it points to the left. Then anything else touching the system? Yes, the rope. The rope is pulling on the system, so I'll draw the tension force. What about the friction between the two blocks? Do I draw it? No, because now both blocks are part of the same object we are drawing. That friction acts inside the object we've chosen. It's an internal force, so we leave it out. How about the normal force between those two blocks? No, that's also an internal force, so we leave it out. Notice how much simpler this system diagram is. No normal force between the two blocks, no friction direction to figure out. Only the external forces remain. When a problem follows it, drawing a system free body diagram can make the rest of your work much easier. When you draw a free body diagram for the entire system, you only include forces from outside of the system. Internal forces stay inside the system, so we don't draw them. Draw only the interactions between your chosen object and the outside world. So that's the entire process. Remember, don't memorize the free body diagrams, memorize the process. Once you have the process, you can draw almost any free body diagram from scratch. Thanks for watching, and I'll see you in the next video.